So this video is a brief description of the concept of the center of mass. So as we have seen in previous videos, an object can be treated as a particle only when all of its parts move in exactly the same way. And if the object does not meet this condition, then it must be treated as a system of particles. So we will see how the complex motion of an object that cannot be treated as a particle or the motion of a system of particles can be represented by the motion of a point located at the center of mass of the system. So let's take this example. So suppose that a person jumps into a pool while freezing the body. So in this case, we can treat the person as a particle because different parts of his body are moving in the same way. So let's suppose now that the person does a somersault while jumping into the pool. So in this case, different parts of the body are moving in different ways, and so we cannot treat the body as a particle. Instead, it is treated as a system of particles, and the motion of the body is represented by the motion of its center of mass. So the point of the center of mass behaves as if all of the mass of the object is located there and as if the net external force is applied there. And as you can see here, regardless of the person rotating the body, the center of mass of the person still follows a parabolic path, just like a particle. So the motion of the center of mass is like the motion of a particle in projectile motion, okay? And here we have a discrete system of particles, and this is the location of the center of mass. So imagine this system moving as a whole, then you can represent its motion by the motion of its center of mass. So as well as simplifying the analysis of motion, the concept of the center of mass is used to analyze many systems, such as a system of two colliding blocks, so two colliding particle-like objects, and also, for example, a system of two colliding subatomic particles, such as a neutron and a nucleus. So let's consider a discrete system of particles like this one, in which the particles are separated from each other. And for a continuous system of particles, the separation between the particles is very small, such that it approaches zero. And an example is an extended object, okay? So let's go back to the example of the man plus skateboard given in the work energy video, okay? And as we have shown, the man plus skateboard cannot be treated as a particle because different parts of the system are moving in different ways. So as the man is pushing the bar, his arm and hand are moving in a different way than the rest of the body and skateboard, okay? But if the system of the man plus skateboard is considered as a system of particles, then the motion can be represented by the motion of the center of mass, okay? And so the work energy theorem can be applied to the center of mass. And in that case, the work done by the force exerted on the skateboarder by the bar is not zero because the point of application of that force has moved if we apply it to the center of mass. So when the man is pushing the bar, the reaction force by the bar is not considered to be acting on this point, rather on the center of mass point, which is moving as a result, okay? So let's consider a simple system consisting of two particles m1 and m2 moving in space, and suppose that their position vectors at a particular instant of time are r1 and r2. Then the center of mass of the system lies somewhere along the line joining the two particles, and its position vector is given by this equation. And in component form, we may write it this way, okay? And suppose now that the system consists of n particles, then the position of the center of mass is given by this equation. So it is sigma mi ri over the total mass of the system m, okay? So ri is the position of the ith particle. So as an example, let's consider this system of three particles, each of the same mass of 1 kilogram, and we find the center of mass of the system. So first we find the x component of the center of mass, and then the y component. So you see, we find the x position of each mass and the y position, and then the vector sum gives the vector position of the center of mass. And as we said, if we have a discrete system of particles in which the separation between the particles is so small that it approaches zero, then we may consider it as a continuous system of particles. So suppose we have a continuous system of particles like this extended object of mass m. So we divide it into small volume elements, each of mass of delta mi, and the vector position ri, okay? So the position vector of the center of mass at a particular instant is then approximately given by this expression. So for a very large number of particles, when n goes to infinity, we have delta mi will go to 0, right? And so the position of the center of mass is equal to 1 over m, the integration of r dm. And in component form, it can be written this way, okay? So let's consider now the difference between elastic and rigid bodies. So an object is known as an elastic deformable object if the separation between its particles changes when a force is applied to it, okay? But if the change or deformation is so small that it can be neglected, then the body behaves in a way that is known as a rigid object. So a rigid object can be defined as an object in which the separation between its particles remain constant with time despite the applied force, okay? So the object has a constant size and shape. And so the center of mass of a rigid object remains fixed at the same location at all times. So in this video, we'll only consider rigid objects, okay? So in solving problems, it is common to use the volume density, which is defined as the mass per unit volume. And the total mass of a rigid object can be written as the integration of rho dv, okay? And so the center of mass may be written this way for a rigid object. So rho may be a function of position, so it can vary from point to point within the object. And also, if the object has a uniform density, so it's a homogeneous object, then rho is written as total mass over total volume, and it has a constant value. And suppose that the extended object or the continuous distribution of particles occupies a surface rather than a volume, then in that case we would use the surface density rho, and this is the general definition, which is mass per unit area. And if it occupies just a curve or a line, then the linear density is used, equal to mass per unit length. And in the special case of a uniform density, we can use these expressions where sigma or lambda are constant, so they have the same value at each point within the object. Also, the center of mass of any homogeneous symmetric object is at its geometrical center, and it is not necessarily located within the object. So these are some examples of a cube, a cylinder, a sphere, and a donut. So now let's consider this example of a thin rod of length of 2 meters with a linear density that is increasing with x, okay? So to locate the center of mass of the rod relative to O, we use this expression. So we substitute for the dm is lambda dx, and the total mass is integration from 0 to L of lambda dx, okay? And this gives the center of mass is at 1.7 meters. So for the second example, we have a uniform square sheet suspended by a uniform rod, and they both lie in the same plane, and we want to find the center of mass of the system. And so because the sheet and the rod are both homogeneous, the center of mass of each is at its geometric center, okay? So the center of mass of the sheet is at the origin, and the center of mass of the rod is at L over 2, okay? So we substitute for them as two particle masses, and we get the center of mass of the system. So for the third example, we want to find the position of the center of mass of this rectangular plate that has a uniform surface density sigma. So we first find the position along the x-axis and then along the y-axis, and the vector position is given by this equation, and as you can see, it is located at the geometric center because the density is uniform. So for the last example, consider a boy standing on a boat, okay? The mass of the boy is 45 kilograms and the boat is 80 kilograms. And we want to find the distance that the boat would move relative to the origin if the boy moves a distance of 1 meter in this direction. So the length of the boat is 5 meters, okay? So by neglecting air and water resistance, the net external force on the boy plus the boat is 0, right? And so the center of mass of the system must remain at rest. So it must remain at the same position even after the boy moves. So suppose now that the boat is a symmetric homogeneous object where its center of mass is located at its geometric center. So the center of mass of the boat is at a distance of 2.5 meters from the origin, okay? And so the center of mass of the whole system can be found from this equation, which is located at 1.6 meters from the origin. So if the boy moves a distance of 1 meter along this direction, then the center of mass of the whole system is still at the same position, right? Because the net external force on the system is 0. So we substitute here the same value for the position of the center of mass. But now the position of the boy is at 1 meter from the origin, and so we find the position of the boat that moves as a result of the boy moving to keep the center of mass at the same position. So the position of the boat relative to the origin will be now at 1.94 meters, okay? Not at 2.5 meters. So the center of mass of the boat is at this position, which means the displacement of the center of mass of the boat is minus 0.56 meters. So the boat moves in this direction as a result of the boy moving in that direction to keep the center of mass at the same position, because the net external force on the system is equal to 0. So thank you for watching. Please don't forget to like and subscribe, and see you in the next video.